Alright, so last Monday we were at annuity. So we talk about the two types of annuity: ordinary annuity, which means that the constant payment, constant cash flow takes place at the end of each period. And also another type is annuity due. So that means the cash flows occur at the beginning of each period. But our course focuses on the first type, ordinary annuity. So then we talk about the present value of annuity. Actually, once we also said that once we uh, are comfortable with calculating the present value of an uneven stream of cash flows, then actually that's the most general case. So we can apply that methodology to the situation here as well. But since the constant payment, since the payment is constant, uh, in this case, actually, it's gonna be simpler than the general case. Um, so again, we can use at least two methods to calculate the present value of annuity. Formula tables. Um, in terms of formula, we talk about the formula is present value of annuity equals payment times this whole chunk here, which is 1 minus 1 plus interest rate, and then raised to the power of negative t. Again, because we are calculating the present value, so the power here needs to be negative. And then the whole thing divided by the interest rate. So that's the formula approach. And for the table approach, we just denote this whole chunk here with a symbol, which is a present PVIFA, which stands for present value interest factor of annuity at interest rate R and for T payments. Very importantly here, T stands for the number of payments for the annuity. So T does not necessarily equal to the period number of the final payment. So for example, if you have a 5-year annuity, like going back to the case we just looked at, here we have a 5-year annuity, but it just turns out the first payment starts from end of the year, which is actually year 1. So the final payment, the 5th payment, is paid on year 5. But that's because, so here there's no difference between the year number and the number of payments. But that's because the first payment starts from year 1. So suppose the first payment starts from year 2, and you can still have a 5 payments, right? The annuity can continue for 5 years. So in that case, the final payment actually takes place at year 6. So in that case, the final payment, the year number, is not the same as the number of payments. The number of payments stays the same, it's 5 payments. So the power here, this T here, that's the number of payments. So we need to be very, very careful. Actually, I made another video specifically talking about how to solve problems if the first payment, first annuity payment, or later on the perpetuity payment does not start from year 1. So in that case, you should understand that the present value you calculated should be the present value at the time, which is 1 period before the starting period of the annuity. So say it again. Suppose the annuity starts from year 2, and still it's a 5-year annuity, so 5 payments. So the present value is actually at year 1. because that formula here always only applies if the first payment starts from next year. So if it doesn't start from next year, then we have to move our baseline. So if the first payment starts from year 2, then we have to move our baseline to year 1, because when you stand at year 1, then year 2 becomes the first year. So then you can apply that formula to calculate the present value. But you have to keep in mind the present value you just calculated is in terms of year 1. It's not the same as the present value in terms of the true current year, which is year 0. But how can you get the true current year present value? Once you have the present value in terms of year 1, then you can further discount that present value back to the true present to get the present value of that year 1's present value in terms of year 1. So I just want to emphasize again that the T in this formula stands for the number of payments. It's not necessarily the final year number or period number of the last payment. So once we denote this whole chunk by present value interest factor of annuity, then we can check the table, because this is available in the table. So we can also solve out this present value. So that's what we talked about last Monday. I just want you to kind of refresh your memory a little bit. So now let's talk about a kind of a more realistic example. So this is buying a house. So when you buy a house, normally you don't pay the price by all cash, because probably you don't have that much of the cash to pay the whole house price. So normally you will borrow part of the price from a bank. So that's called a mortgage loan. So this is an example of how to use the knowledge of the annuity and the present value of the annuity to determine the maximum price you can offer to buy a house. So let me read the setup. You are ready to buy a house, and you have $20,000 for a down payment and the closing costs. So you can imagine this $20,000 is like your savings. So the closing costs are estimated to be 4% of the loan value. So what is the closing cost? Closing cost generally means that if you buy a house, in addition to paying the price of the house, you also have to pay a bunch of other fees. For example, the government, you have to pay the taxes to the government, or you have to pay the fees to attorneys, or some other like loan origination fees. Those kind of fees are all considered the closing cost, and you have to pay those costs upfront. So here the setup tells us closing costs are estimated to be 4% of the loan value. So that means if you can figure out the loan value, you can also figure out the closing costs. And you have an annual salary of $36,000. So that's an annual salary. So basically, if you divide this by 12, you can figure out the monthly salary, and that's easy to do, right? It's $3,000 per month. And the bank is willing to allow your monthly mortgage payment to be equal to 28% of your monthly income. So normally, some people say that to be safe, it's best that your mortgage payment will not exceed 1/3 of your monthly salary. So that's like so based on this percentage here, it's close to 1/3. So that's like the recommended maximum mortgage payment. So that means don't make like 80% of your monthly salary to go to mortgage. So that means that you probably have have purchased a price which is too high based on your salary. And so the interest rate on the loan is 6% per year with monthly compounding. Uh, So I made another video file also talking about non-annually compounded case. So this is actually one of the examples for that. So here we have a monthly compounding, but 6% here, normally by convention, the interest rate given is always in annual terms. So we call that the annual percentage rate or APR. So if you have applied the credit cards in the past, the interest rate offered by the bank for your credit cards most likely is going to be APR. So APR is the quoted rate. So this doesn't necessarily mean that by the end of the year, if you put $100 in the bank, by the end of the year, your interest will be $6. So here the 6%, if it's not compounded annually, then the 6%, which is the quoted rate, does not necessarily tell you. Actually, in most cases, it doesn't tell you how much you're going to earn for your investment. So that's why we have this term quoted rate or APR. Um, there's another interest rate which is called APY, annual percentage yield. So that rate tells you how much you're going to earn based on your investment. So if that rate is 7%, that means by the end of the year, your interest will be $7 if you put $100 down, um, regardless of the number of compounding periods. So here we have a monthly compounding, and this 6% is the annual term. So that means we can divide this 6% by the number of compounding periods within a year. So here we have monthly compounding, so we have 12 compounding periods within a year. So 6% divided by 12, that gives us 0.5%. That's the monthly interest rate. So what matters here is the monthly interest rate because the interest is paid every month for a 30-year fixed rate loan. So the year is the mortgage loan is 30 year, and that's like the most common case. And we can also have like a 15-year loan or 10-year loan. But 30-year loan is like the most common case. Um, so to be consistent, you cannot work with monthly interest rate, but with number of years. So you also have to convert this 30-year to the number of months. Obviously, that's easy to do. Just multiply that number by 12. So you have 360 number of months before you have to pay off the loan. So how much money will the bank loan you, and how much can you offer for the house? So the one particular feature of the mortgage loan, we'll be talking more about that when we talk about the amortized loan in just a few minutes. One particular feature of the mortgage loan is that every month your payment will be the same. It's going to be a constant payment. Actually, here you can see it's going to be 28% of your monthly income, and your monthly income stays the same, right? It's $3,000 based on your annual salary. So that also means that your mortgage payment is constant every month. So that's a feature of mortgage loan, what we call the amortized loan. So amortization means that you borrow some money upfront, but you pay back the money with constant payment over a certain number of periods. So here over 360 months or 30 years, you pay back the loan. So that also suggests, because remember, when you borrow, you have to pay back the principal, right? And also you have to pay the interest. So this particular feature of constant periodic payment already suggests that every period your fixed payment includes part of the principal and also includes part of the interest. Actually, there's a pattern for the trend of the principal portion of the payment and also the interest portion of the payment. We will be briefly talking about later. So now let's, how can we solve this question? So in the next slide, you can see my solution. Well, we actually already figure out much of these numbers. So monthly income, that's $3,000, and maximum payment, that's based on 28% of your monthly income, which is 0.28 times 3,000. So that gives us 840. So that's your constant mortgage payment. So from that payment and from the number of month for the mortgage and for the monthly interest rate, and then you can figure out the present value of that mortgage loan. And that present value basically is the loan amount you borrowed upfront. So from that formula, we can just plug in the formula. This is the payment, 840 times 1 minus 1 over 1 plus the interest rate. Again, here we have to work with the monthly interest rate, which is 0.5%. So that's 0.005. So 1 plus that becomes 1.005, and then reach to the power of uh, here we have 1 over that, so the power here needs to be positive. Otherwise, if we don't have 1 over there, just a 1 plus interest rate raised to the power, then the power needs to be negative right here. So the power is positive 360. And then divide the whole thing, 1 minus that by the interest rate, the monthly interest rate, 0.005. So that's how we get this $140,000, 105. So that's the loan amount. But when you buy a house, you also have to put some down payment. Put down some what they call the down payment. So that's like a fraction of the house price. So here the setup tells you that um, you have $20,000 for a down payment and closing cost. So that means the sum of the down payment and the closing cost is $20,000. So then how can you figure out, the question is asking how much money will the bank loan you. We already answered that part by calculating the present value of this mortgage loan. So we know that it's going to be 140, something like that. So the next question is how much can you offer for the house? So how much can you offer for the house? We have the mortgage loan amount, so that's how much you borrowed. That's part of the purchase price. But also since you also have to put some money down, so that's your down payment. So the offer price is the sum of the down payment and the mortgage loan amount. Because we already know the mortgage loan amount, so the next job is to figure out what's the down payment. But here the question tells you that the sum of the down payment and the closing cost is $20,000. So if you can figure out the closing cost, you can also easily figure out the down payment. And the setup further tells you that the closing costs are estimated to be 4% of the loan value. So the loan value, we already figured that part out. That's the present value of this mortgage loan, which is 140, 105. So from that information, we can figure out the closing cost, 4% times that loan value. So that's how we get this $5,000, 604. And hence the down payment is the difference between your total savings, $20,000, and minus this closing cost. So that's how you get this 14,396. So finally, the total offer price you can purchase the house for is the loan value plus the down payment. So that's how you get this 154,501. Of course, most likely you're gonna most house purchase price is not like in it's most likely it's gonna be in the hundreds. So the offer price most likely will be 154,500 rather than 154,501. Right, it's gonna be so that's the most likely case. So from this example, you can probably better understand by using the knowledge of the time value of money and particularly the present value of annuity, we can determine the maximum price we can offer for our house. So if more people understand this point, especially back to probably 2007, 2008, where we have the financial crisis due to the mortgage, subprime mortgage loan, probably we could have avoided or at least reduce the magnitude of the crisis. I think one of the reasons for the crisis was because many people they didn't understand based on their earning power, based on their salaries, how much they can offer, how much they can they can afford to a house. They probably have purchased a house which is too expensive based on their salaries. So if somehow the economy doesn't do so well, so they lost their job. So immediately they will feel difficulty in paying the mortgage loan. And if many people have the same situations, then the economy will experience a downfall. I hope that by using the knowledge we learned in finance, we can make more rational personal decisions as well. Okay, so that's the example we just talked about. Amortized loan. Actually, we already talked about based on what is amortized loan, and we also briefly talk about that. So some other examples of amortized loan include if you borrow to finance your study at the University of Baltimore here. So once you graduate and find a job, then you have to pay your loan back. So that student loan is also an example of amortized loan. And if you buy a new car, and you can also finance your purchase with amortized loan. So every month you're going to pay a constant payment until the loan is fully paid off. Um, so reducing the balance of a loan via annuity payments is called amortization. So now let's work with another question, which I want to show you not only how to calculate the fixed payment. So here, amortized loan is also a type of annuity. But here we're not concerned about calculating the present value of that annuity. We're more concerned about calculating that fixed payment, because the present value is given, right? That's how much you borrowed from the bank. So that's given. What you want to figure out is based on what I borrowed, how much I need to pay back every month or every period in order to fully pay off the loan. So that's our primary interest here. But either amortized loan or general annuity questions, they are based on the same formula, which is the present value of the annuity. So it's just solving for different unknowns. So here we are solving for the payment based on the present value. And there we are provided with the payment, and we want to solve for the present value. So let's look at this example. If you want to finance a house purchase, again, this is the house purchase example, and the house purchase is priced at $300,000 with a mortgage loan of $240,000 to be paid off in 30 years. So again, the mortgage loan amount, in generally speaking, is less than the house price because you have to pay some down payment. You have to make some down payment, right? That's the reason you want the bank wants you to make the down payment is because they want the house price, the house value to be above the amount you borrow from them, so they can have some type of security. So if you cannot pay back the mortgage, then the bank have to take over the house, but they want to make sure that the house value is sufficient to cover their loan value. So that's why they want you also to pay some money down. So you want to the mortgage loan is $240,000 and it's a 30-year loan. So here we are also working with the month. So 30 year is 360 months, at the interest rate of 3% compounded monthly. So again, if the question doesn't specifically mention monthly interest rate, always assume the interest rate is annual. So we should divide this 3% by the number of months within a year, which is 12. So that will give us 0.25% for the monthly interest rate. And what will your monthly payment be? So this is actually a typical annuity question, but the two features which are different, slightly different from what we have done so far. First, actually this feature we probably is not the first type we encountered, is a non-annually compounded interest rate, right? Mortgage loan example, there we also had a monthly compounding. So here we also have monthly compounding. So those are examples of a non-annually compounded case. So that's the first feature, which might be slightly different from the other examples we looked at. And the second feature is that, as we said, for the amortized loan, we are concerned about solving for the constant payment rather than the present value of the annuity. So but it's based on the same formula. Based on the present value of the annuity. So we know that equals payment times 1 minus 1 plus interest rate, which is the power of negative t, and the whole thing divided by the interest rate. So now, let me just fill in these blanks so we can solve out the payment. So here we know that the mortgage loan amount is 240,000, right? The house price is 300,000, and the mortgage loan is $240,000, and that equals payment 1 minus 1 plus, again we have to work with the monthly interest rate, which we just calculated, which is 0.25%, and raised to the power of negative t. T here is the number of months, which is negative 360. So now I have to work, put this as the superscript. So you shouldn't confuse that with, so why don't I, excuse me, why don't I put a parenthesis sign? So you may have less trouble in understanding it. So that's in the power function, at the power rather than its product. Okay, so that's the 1 minus 1 plus the interest rate raised to the power of negative t. And this whole thing divided by the interest rate, 0.25%. Okay. Oh, it's best to be consistent. The square. Okay, so that's when we plug in the numbers into this formula. So now we can solve out this payment, right? By dividing both sides by this chunk. 1 minus 1 plus the interest rate raised to the power of negative 360 divided by 0.025%. If we do that, we can solve out this payment to be that's gonna be $111.85. So that means based on the purchase price, based on the house price, and based on the number of years for the loan, our monthly payment will be $11.85. So that's how much we have to pay for the loan every month. So now the next question I want you to figure out is, since we mentioned the mortgage loan means that every month, every period. The payment is fixed. So this $1,011.85 is fixed for every month and until the loan is paid off. But if you borrow, you have to pay back interest plus principal, right? So this fixed payment here suggests that this payment every month includes both principal and interest. So our next question is what proportion of the payment is principal and what proportion of the payment is interest? So obviously this will take a long time. If you want to figure out fully this 360 months of principal and interest. So we just work with the first 2 months just to have some idea about this pattern of the principal and the interest portion of the payment. So so what I mean here is we have let's say we have a month. Let me make a table here. The month table. This is the month number, and we have every month. Obviously, the payment will be constant, right? Let's just work with 2 months, month 1 and month 2. And based on our calculations, month 1 the payment will be $1,011.85, and month 2 will be the same, right? Because it's a mortgage loan, so every month the payment will be the same, $1,011.85. So now we are interested in what is the portion of this payment which goes to principal, and what portion of that is interest. So let's first figure out the interest portion of that, and then we figure out the principal. So what about the interest portion of that for the first month? The interest portion should be the initial principal times the interest rate, right? So initial principal is a 240. You borrow $240,000, and the monthly interest rate based on our calculation is 0.25%. So the first month interest is easy to see. That's this amount, which will give me the number 600. So that means 600 of this $1,011.85 is interest portion. So the remaining must be principal, right? So that means that the principal has to be the difference between your fixed monthly payment and the interest portion of that payment. So that will give me $411.85, right? So that's how much you pay in the form of principal. So once you pay back this much of the principal, of course, you're also reducing the remaining principal. So now let's also calculate in the remaining. Oh, sometimes it's not very beautiful. Remaining. Let me just use a PRIP. Okay. Remaining principal. So that's gonna be your initial balance, 240 minus 411.85. So that will give me how much? Let me look at my that's 239,588.15. Let me double check. Yes. So now let's work with the month 2. So for month 2, the interest should be the remaining principal, right? Remaining principal from month 1 times the interest rate. So that's gonna be 239,588.15 times 0.25%. So that gave me 598.5. Hence, the principal portion of the second month's payment will be the difference between this constant payment again and this interest portion. So that gives me the principal portion will be 413.35. Hence, the remaining principal is the difference between the remaining principal from month 1, which is 239,588.15, minus the principal portion of the payment from month 2, 413.35. And you can figure out how much this is by pulling out your calculator. Just for the time, I don't want to do that again. But I want you to observe the pattern of the interest portion and the principal portion. And you can continue this third month, 4 months, or 5 months until we have 360 months, right? So this table will be very, very long if you want to fully complete it. But of course, there's a pattern, so you don't have to actually write down all these numbers like what we did. Here, I just want to show you how exactly we can solve this amortization schedule problem. So if you look at the interest portion, you can see that it's declining over time. And conversely, the principal portion is increasing over time. So even without calculation, can we understand the reason for that? I believe so, right? If you think about that, interest portion of a certain month's mortgage payment is the remaining principal from the previous month multiplied by the interest rate. So the interest rate is fixed, but the remaining principal is going down over time, right? Because you are paying off the loan over time. The loan balance should be lower and lower when you pay the money. So because the remaining principal is declining over time and the interest rate is fixed, so that means the interest portion of the loan, of the mortgage payment, is also declining over time. And you can see even with these 2 months numbers, and we can see that pattern here. And because the interest portion and the principal portion, their sum has to be fixed. This payment here is fixed. So if the interest portion is declining over time, so that means the principal portion has to increase over time. And that's the pattern here, right? The principal portion is increasing over time. And if you complete this table, you can also confirm this pattern. So let's go back to this slide. So what we just discussed can be put in this graph. In this graph, this height of the box stands for the constant mortgage payment. So here is the horizontal axis. You can see this is like the horizontal line here stands for the number of payments. So this height, because it's fixed, so that means that every period, the mortgage payment will be fixed. But this curve, this red curve, divides the proportion of that payment which goes to interest and the proportion of that payment which goes to principal. And based on our discussion, the interest portion has to decline over time. So you can see that this curve, red curve, is declining. It's a downward sloping curve. And the other part, which is the principal, is increasing over time. But their sum is then like the height of this box stays constant. So that's the mortgage, amortized loan mortgage payment every month, every period. It's going to be fixed. So that's the general pattern of the interest portion and the principal portion. And so our next topic is perpetuity. I probably spend too much time on this because I want you to have a very thorough understanding for the annuity. This is very important, even though it may look simple from some perspective, but when you look at some questions, it's going to be another issue based on my experiences. So perpetuity is a very special type of annuity. So if we understand annuity, we can also understand perpetuity. So perpetuity is special in the sense that uh, annuity, generally speaking, the number of payments is finite. For example, we can have 5 payments, 10 payments, or even 100 payments. But the point here is that it's finite. It's a finite number. But perpetuity, we actually have an infinite number of constant payment. So that constant payment lasts forever. So you may ask, what in reality, what kind of investment have this feature? You may be wondering, do we really have such an investment? Actually, we do, even though compared with annuity, it's relatively not that common, but we do have cases for perpetuity. So two examples is one is British government back in 1770, I believe. They issued a security, and now we have a name. We have kind of the name for that security is called council. So it's a type of bond. So it's let me write down this name, CONSOL. So that's back in probably 1770s, like that. So the British government issues a council, and that council is a kind of a perpetuity, because that bond pays the lender interest rate forever. So even nowadays, that bond is still paying the interest, the coupon for the lenders. Even though the interest has been adjusted over time, but it's still there's no maturity associated with this council. So that's one example of perpetuity. And another example is what we call the preferred stock. We're talking about this preferred stock uh, next next week, next session 5. It's one kind of stock, and the particular feature of this stock is that it has constant dividend payment. So the dividend is fixed, and there's no maturity. So in theory, preferred stock is also a type of perpetuity. Even though in reality they can be recalled. So even though they don't have a specific maturity date, but the firms who issue preferred stock, they can recall, they can call the existing preferred stock back. In reality, their maturity can also be fixed. But in theory, it can last forever. So that's another example of perpetuity. So now we are concerned, our interest is how do we figure out the present value of the perpetuity. So if you are provided the perpetuity, for example, every year, you are entitled to receive $1,000, and that can continue forever. So you probably should ask the question, what is the value of that investment for me, right? So there we are interested in the present value of that perpetuity. So because perpetuity lasts forever, so you may be tempted to think that the value or the present value of the perpetuity is also infinite, right? Because you have constant payment and not last forever. So probably the value is also infinite number. But it turns out that's not the case. Even though that the payment, for example, $1,000 continues for 1,000 years or 2,000 years, an infinite number of years, the value today is a finite number. So to understand that, you can simply calculate, given a certain interest, you can calculate, for example, like just, that's interesting. Hmm. Okay, so I guess this is preventing me from operating it. So I guess you can do your calculation on your own. You can pull out your calculator and do a calculation. What is the present value of the the 1,000 years payment? So let's say every year you are entitled to receive $1,000. And 1,000 years later, what is the present value of that number, $1,000, given the interest rate of, let's say, 2%? So pull out your calculator and do the calculation. And by now you should be comfortable with doing that type of calculation, right? And you can see that the present value of that number is almost zero. And because it occurs in so distant future, so the present value of that number actually is very minimal. So even though the annuity can last forever, but the present value of that number, the perpetuity, sorry, the perpetuity lasts forever, but the present value of that perpetuity is not finite number, because the very distant constant payment, for you the value is almost zero. So that's why the present value of that annual perpetuity is not an infinite number. So now let's the present value here is actually is easier to calculate based on compared with the annuity case. It's simply the constant payment divided by the interest rate, periodic interest rate. So let's look at this example. What is the present value of $2,000 perpetuity discounted back to the present at 10% interest rate? So based on the formula, it's simply the payment divided by the interest rate, right? It's $2,000 divided by 10%, which will give us the $20,000. So this is easy to do. So finally, I think we already talked about this. Sometimes we may have a non-annually compounded interest rate. So in those cases, how can we solve out either the present value or future value, or sometimes the payment, the constant payment, if it's amortized loan? All right, so for those cases, the technique is actually very similar. So instead of figuring out the number of years or annual interest rate, now you just will have to work with the number of periods. For example, if it's quarterly compounding, then you have to figure out the number of quarters and also work with the quarterly interest rate rather than the annual interest rate. So that's the only difference. I think we already talked about a lot about this, so I'm gonna skip this. Um, so let's directly look at this example. Computing payments with APRs. Suppose you want to buy a new computer system and the store is willing to allow you to make monthly payments. The entire computer system costs $3,500. The loan period is for 2 years, and the interest rate is 16.9%, and this is called annual percentage rate or APR, as we just talked about. Without specifically mentioning it, you should always assume the interest rate quoted is the annual rate with monthly compounding. So again, because it's the quoted rate or APR, this number doesn't tell you that if you put $100 down, your end of the year interest will be $16.09. That's not the case, 90 cents. This doesn't tell you how much you're gonna earn, and that's why we call it quoted rate. So here we have monthly compounding, which means that instead of being paid interest every year, we are being paid interest every month. So based this interest rate, this APR can tell you how much we can earn every month. That's simply by dividing this interest rate, 16.9%, by 12. That gives us the monthly interest rate. So here we need to work with the monthly number, monthly payment. But other than that, I believe this question is straightforward to solve. Right, the entire computer system, the cost, that's like the present value of this. This is the amortized loan case. So this is the present value of the amortized loan, and here the loan lasts for 2 years. But then again, we have to work months. We have to work with months. So 2 years translates into months, equals 24 months. So that's the number of payments for the loan. And interest rate, then we have to work with monthly interest rate, 16.9% divided by 12. Here, I want you just to note, to remind you, do not round this number. Do not round 16.9% divided by 12. If you round that number, probably you get a final answer which is sometimes can be significantly different from the correct answer, because the interest rate will have a dramatic effect on the final answer, especially when the number of payments is large. Here probably it's not a big deal because the number of payments is only 2 years, which is 24 months. But sometimes if you have like a 30-year loan, like we just looked at, so which is 360 months, then the rounding issue regarding the interest rate will have a dramatic effect on the final result. So from that regard, I do not recommend you to round this number to get the intermediate answer. Rather, you can just input this 16.9% divided by 12 directly into your calculator and get the final answer. Okay, so let me just fill in these blanks, give you the final answer. I believe by now you should be comfortable in solving this type of question. So the monthly rate, again, it's 16.9% divided by 12. Based on our discussion, we just put the number like that. We do not directly calculate out this number. So the number of months, which is 24, and finally, actually we also should have mentioned should also the present value of the loan. That should be the 3,500. So plugging this into your 3,500 equals payment, right? Times 1 minus 1 plus 16.9% divided by 12 raised to the power of negative 24, right? Because we are calculating the present value. So then divide the whole thing by the interest rate, 16.9% divided by 12. So that's how we plug in these numbers into the equation. And now you can solve out this payment, right, by dividing both sides by this whole chunk here. And then you can solve out this payment to be $172.8. So you can double check whether you can get the same answer as this one, and believe that's the end of this session.